All right, in this second part of section 7.1, we are discussing an extremely important topic, the sampling distribution. And what is a sampling distribution? It's this is really beginning the really abstract concept of a sampling distribution in the importance of being able to calculate probabilities um, based on samples that we take. So it's very abstract. Hopefully you've read through section 7.1, and this isn't your first go around as far as understanding the sampling distribution, but it is a fairly abstract concept. And so let's get started. All right, in this part, we're going to figure out what is a sampling distribution. And we're going to distinguish it between the other types of distributions that we'll be talking about. So the distribution of a population, the distribution of a sample, and then the sampling distribution of a particular statistic. So the statistics we'll be talking about are p hats and x bar. Those are the two different statistics that we'll be dealing with mostly. And then we'll decide whether or not a particular statistic is an unbiased estimator of its parameter. And then we'll talk about variability and the relationship between variability and sample size. Okay, so I have a bag of chips and that I generally pass around the room, and it has a bunch of chips in it. And it has red chips, I think maybe some pink ones as well, but it also has some blue chips. And so let's assume that if we have time, of course, I would have passed this around the room and everyone would take a sample. So everyone would shake up the bag of chips and they would randomly draw out 20 chips. And then they would count the number of blue chips and record their p hat. So their p hat, or sample proportion, would be the sample proportion of blue chips in their sample of 20. So they might pick out just one blue chip, or they might have two blue chips, or three blue chips, or so on. And so we would do that, and then everyone would record it, and then I would go around and ask everybody for their p hat. Okay, so let's assume that I've done exactly that. And so I've asked all 77 of my AP Statistics students to select a random sample. Everyone did 20 chips out of the bag of chips. And then I'm going to ask everybody for their p hat. Remember that p hat looks a lot like y hat, which is the predicted y value back when we were dealing with scatter plots. But here, remember this P with a little hat above it is the symbol we use for the proportion of a sample. And so I would go around the room and ask for everyone's P hat. What was the proportion of blue chips in your sample of size 20? And so I plot all 77 of those in a dot plot, and you can see here we have what looks to be a fairly symmetrical, maybe not perfectly normal, but certainly bell-shaped. Okay, so each one of those dots, there's 77 of them, each one of those dots represents one of my students' p hats for the picking of the blue chips out, picking of the chips out of the bag. And so the p hat is the proportion of blue chips in their sample. So you can see that some students got, one student got as low as 25%. A couple students got as high as 75% blue. Most of the students are kind of in the middle here with something around 0.5. Okay, so now, what if Mr. Rogers, because we don't know in this bag of chips, we don't know what the true proportion or p value is, the proportion of blue chips in the population. So the sack or bag of chips that got passed around the room, was the population, and we don't know what the true proportion of blue chips are in that bag. All right. So what if I told you, what would your reaction be if I told you that there are 20% blue chips in the bag? Looking at our dot plot, what would be your reaction if I said, oh, that population from which you sampled, from which everyone sampled, the true proportion, P, is 20%. So you would probably say, that's not very likely, Mr. Rogers, because you can see there's not a single sample at 20% or more extreme than 20%, right? So it's not very likely. In our 77, we didn't have any. In our 77 samples, we didn't have any samples as low or lower than 20%. So that's telling me that it's not very likely that what Mr. Rogers said is true for A. The true proportion of blue chips is probably not 20%. What if instead I said it was 70%? Well, we would want to look at the high end and say, okay, well, how many were at 70% or larger, right? So we have five chips out of 77, and so that's like 6.5% of our samples were as extreme or more extreme than 70%. Not unheard of, but not very likely. Still, it's possible, but probably we wouldn't have gotten all of the outcomes we got that are showing up in our dot plot if the true proportion of blue chips was 70%. So I guess now what I want you to do is tell me, like, okay, so what do you think? Based on that dot plot that we have from our 77 samples that we took in class, in all my classes, what would you guess the population proportion of blue chips is, for the whole, the bag of chips? What's the proportion of blue chips in the bag? All right, and so you would probably guess that it's somewhere around 50%, right? I mean, in here we've got a lot of the results, the p hats, are kind of, between 45% and maybe 55 or 60. Somewhere in there is probably where the true proportion of blue chips are, right? Now, we don't really know because we don't know what the population was, but it's not very likely to be 20. None were that low, and it's not very likely to be 70. Only 6% were as high or higher than 70%. So it's probably not that as well. Okay. Now this dot plot that we have here is not really what we call a sampling distribution, but it's kind of beginning. We might call it a trial or an approximate sampling distribution. Sampling distribution is if we were able to take every possible sample of size 20 from that bag. So it would be like a combinations type thing. How many possible samples of 20 out of 200 chips, how many different samples of 20 out of a bag of 200 are even possible? We're talking about trillions and trillions of different samples. So we're never really going to be dealing with a true sampling distribution. We're going to be dealing with approximate sampling distribution. So this is an approximate. It's 77 samples. It's not a whole lot, but it's beginning to sort of look like a sampling distribution, or at least an approximate sampling distribution. Okay, so now let's assume that I continued passing that bag around and we got 500 samples of size 20. So now I've got a plot here that sort of is even bigger, right? It has even more. Now these are all dots, but there's so many dots and they're so close together that they kind of look like vertical bars, but those are just dots, okay? So we have, now I'm telling you, okay, we have, we took samples of size 20, And the population was half red and half blue. So the true proportion is 50%. All right, what is that one dot at at 0.15? So that would be this dot here. What does that represent in this context? All right, so that one dot represents one of the 500 samples, and that one dot, that one sample of 20 chips had only 3 that were blue. So that gives us a p hat of 15%. All right, now, would you be surprised if I told you, would you be surprised if you got a p hat? Like I give you the bag, you take out a sample, and your sample is 85%. Should you be surprised if I tell you that the bag, right, the bag that you've been sampling out of, and then we took all 500 of these samples, is 50% blue, then we would expect to get a dot plot like the one that's showing here on this slide. So would you be surprised to get a p hat of 85% or higher if you took a sample of size 20 out of the bag? Okay, so I think you would be surprised, right? Because there's only 85, that's this spot out here. There's nothing at 85 or higher. So none of our sample of sample size of 20, the 500 samples, none of them had 17 or more blue chips that would give us a p hat of 85% or more. So yeah, you should be surprised. Out of 500, we never got a single one. So if I give you a bag of chips and it happens, then that's kind of telling us that it's probably not 50%, because we know it's so unlikely to get a sample of size 85, a sample with not a size, but a sample of a p hat with 85% blue chips out of a bag that's really 50-50. All right. So yeah, we should be pretty surprised. All right, what about part C? So Mr. Rogers claims to have 100 red chips and 100 blue chips in the bag. If a classmate randomly samples 20 chips and 18 of them are blue, what would you conclude about the population and about Mr. Rogers' statement? All right, so it's not very likely, right, that is possible. So if we say 18%, that's 90%. So there's no dots at 90 or any further up with when we took 500 samples from a population that was 50% blue, 50% red. We never got anything as extreme as 18 blue chips or 90%. So this would be, and if we get it, it's so unlikely, then that's evidence that the true proportion of blue chips is actually higher than 50%. Because if it was 50%, we would expect to never get, out of 500, we would never expect to get one sample of size with a p hat of 90%. So if we got one that was that high, a p hat of 90% or more, that would be strong evidence that the true population proportion is actually not 50%, but is actually dragged up closer to our p hat of 90. Can't say that that the true proportion is 90 necessarily from one sample, but it would be evidence that it certainly would be higher than 50% and up closer to our p hat. All right, so sampling variability. So the question is, how can X bar be an accurate estimate of mu? So we saw that we could have lots of variabilities in our samples. After all, different random samples produce different values of X bar. So if I were to take several samples and look at X bars, the sample mean in all those, I would expect them to vary. All right. And so every sample is going to vary from every other sample. You're never going to get the same sample statistic or X bar when you sample. And so this is referred to as sample variability. So to make sense of sampling variability, we have to ask ourselves, what happens if we take many, many samples? So we sample, we sample, we sample, we sample, we sample. We take lots and lots of samples. We want to think about, well, what happens when we do that? All right, so if we took every one of the possible samples of size n from a population and calculated the sample proportion for each, or the sample mean, depending on which statistic we want to talk about, and then graphed all those values, we'd have what's referred to as the sampling distribution. So the sampling distribution is something that's theoretical. We never really sample every possible sample. We never even sample 500. In reality, we would never even sample 77 like we did in class. All right. What we do is we think about what would the distribution of all the possible samples look like. And so that distribution is referred to as the sampling distribution. All right. So sampling distribution of a statistic. And for us, that's going to be either X bar, this mean, or P hat, the proportion. So sample proportion or sample mean. So the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of that same size, whatever size you're talking about, all right, from that same population. So if we were to theoretically be able to take every single sample of a certain size from a population and plotted all of those sample statistics, we would have the sampling distribution. So it's a distribution of all possible samples. All right, and so then we take a sample and we can compare where our sample would be in that distribution to make some estimates as to whether we think a particular population parameter is valid based on the sample statistic that we get. All right, so in practice, it's difficult to take all possible samples of a certain size to obtain the actual sampling distribution. We never do this. Actually, in one of your homework assignments, they're gonna ask you, because the population is so small in this homework assignment, that it does actually have you create the sampling distribution, the actual sampling distribution. But most of the time, it's going to be a theoretical thing, and we're gonna take many, many samples. We'll call those approximate sampling distribution. So we'll try to imitate this process. So we're going to try to imitate the process, and we'll take many, many samples, but we will not take all possible samples in almost every situation. Again, except for that one homework assignment that they're going to ask you. They give you a population, and then you are going to create the true sampling distribution. It's not going to be, on a magnitude of trillions and trillions of samples. It's just going to be a handful of samples. All right, so it's pretty important that you understand the difference between these three things here. Three different distributions. All right, we have a population distribution. Typically, we don't know what this really is. Like in our bag of chips, often we don't know what the true proportion of blue chips in the bag is. And in reality, in the real world, we won't know what the population distribution is, but there is a thing called the population distribution. And then there's the distribution of the sample. So you take a sample from that, and we could make a plot sometimes or graph from the actual sample, one sample. So when we talk about the distribution of sample data, that means you took one sample and you're looking at the graph or the distribution of that one sample. And then the sampling distribution, that's what it would look like if we were able to take all of the possible samples, so all the p hats, all the possible samples and all the resulting p hats or X bars from all those possible samples, and we plot those. That's the sampling distribution. Very important. The sampling distribution and the distribution of the sample are totally different things. So you cannot confuse those terms. you will lose major points if you say something like distribution of sample when you mean to say the sampling distribution. Totally different things. Make sure you understand the difference. Okay, so here's a visual of what that last slide was talking about. So let's assume we have a bag of blue and red chips. Let's assume we know the population is 100 of each. The proportion of blue chips is 50%. Then we could take a sample. In this case, we've taken 3 samples. We could take lots and lots of samples. And in each of those samples, then we could, however many we take, we could plot them. And so in the example that we have 500 samples, 500 samples. So that's not really a sampling distribution. That would really be an approximate sampling distribution. All right, so the approximate sampling distribution, because this is not all possible samples, but 500 samples. All right, now in reality, we're not even going to do that. We're going to take 1 sample, but it's good for us to understand what the distribution of all possible samples looks like. So that way, when we get our sample, our 1 sample, we're going to be able to make conclusions about whether we think the population proportion is actually 50% or not. All right, the fact that statistics from random samples have definite sampling distributions allows us to answer questions about how trustworthy is a statistic as an estimator for a parameter. All right, to get the complete answer, let's think about what we usually look at: center, spread, and shape. So the center, biased and unbiased estimator. So in the blue chip example, we collected many samples of size 20 and calculated a sample proportion of blue chips. How well does the sample proportion estimate the true proportion of the blue chips, or P? So let's look at this, for example. Note the center of the approximate sampling distribution, that one where we took 500, looks to be pretty close to 0.5. And in fact, if we were to take all possible samples of size 20, so this is using that whole idea we talked about the other day in combination. So we have 200 chips in the bag. We want to select 20. How many different ways can we do that? That's a combination of 200, choose 20. And that's 1.6 times 10 to the 27. That's like more than a mole, right? And we're talking about a 1.6 and then move the decimal place 27 times. I mean, it's a huge number, right? And so that's how many we could how many samples we could possibly get. All right, we would find that the mean of the sample proportion, so in other words, the dot plot that we have, right? It would be a normal curve. The middle, or the mean of that sampling distribution, the mean of all of the sample proportions would exactly be 0.5. All right, and then, so this is the kind of the beginning of the idea of what we call an unbiased estimator. So a statistic used to estimate a parameter is an unbiased estimator if the mean of the sampling distribution, again, ours pictured here is an approximate sampling distribution, but the mean of the sampling distribution is equal to the true value of the parameter being estimated. Okay, so that means we would expect this normal curve, which is the sampling distribution of the p-hats, its distribution, the normal curve, will be centered at the true parameter P, or 50%, because 50% of the chips in the population were blue. So we would expect not every sample that we take to have a p-hat of 50%, but the distribution of all p-hats that would be possibly taken would be centered at that same p-value, 50%. All right, spread. Lower variability, of course, is better. We get trustworthy estimates of an unknown population parameter In order to do that, start by using a statistic that's an unbiased estimator. So we want to make sure that we're using p hat. It's an unbiased estimator of p. And we want to use x bar, which is an unbiased estimator of mu, the population mean. All right, so first start with an unbiased estimator. That's what you want to do for sure. This ensures that you won't tend to over or underestimate, because the center of our sampling distribution will be at the value we're trying to estimate. Now, unfortunately, using an unbiased estimator does not guarantee a value that's going to be close to the actual parameter value we're trying to estimate. But if we look back at our chips example, let's say that instead of picking 20 chips, I had everybody just pick 2 chips. So how good of an estimator would this be? Well, sometimes if I choose 2 chips, I'll get 1 blue and 1 red, and that would give us, you could see the high peak there at 50%. So that's this here at 50%. But sometimes, you can envision if a bag of 200 chips and I pick 2, I could often get no blue chips. So that would be these here at 0. And then these here at 1 means that both chips were blue. So you can kind of envision, I think, situations where those would happen. However, so the whole point is this is quite varied, right? So I get values in our sample varying from 0 all the way up to 1. So the range of values in our samples is quite large. That's not good. If I instead go to a sample size of 20, then it's not very likely you get 0 or 100% blue chips. So more likely you get values in the middle. So these are better estimates. All these p hats in the middle are better estimates of our true proportion because our sample size was larger. We're not going to get things way to the extreme over here at 0 or 1. We get things much closer to the true proportion of blue chips of 50%. And so the whole point of this slide is larger sample sizes give us smaller variability. All right, and so that's basically what I'm trying to say here. Larger samples have a clear advantage over smaller ones. They are much more likely to produce an estimate close to the true value of the parameter. So sample sizes of 2, no good. Sample sizes of 20 did a much better job of estimating that, that true proportion of 50%. Okay, so when we are talking about the sampling distribution and how spread out it is, it's really going to be dependent on the size of the sample. It is maybe not intuitive, but it really does not depend on the size of the population. So that if I sample from a population of 1,000 versus a population of 100,000, the size of the sampling distribution, or the spread, I suppose I meant to say, how spread out that sampling distribution is not going to depend on the population, with the caveat that, of course, you are never going to sample more than 10% of that population. But let's say we have a sample size of 20. It doesn't matter if my population is 100,000 or a million, or even 1,000, right? So if I'm sampling 20, a population of 1,000 and a population of 100,000, it really won't matter. It doesn't come into the equation, or any kind of, doesn't affect at all the spread of the sampling distribution. Of course, we have to assume that we're not going to ever sample more than 10%. So the general rule is, of course, then that the larger the sample is, the smaller the spread of that sampling distribution. So larger samples give smaller spreads for our sampling distribution. So that means that a larger sample is more likely to be closer to the true proportion that we're trying to estimate than smaller samples. All right, so we have sort of two things that we want to talk about here, and they are variability and bias. So ultimately, if we think about, if we were using, like, I don't know, shooting a bunch of arrows at a target, and we want to look at high bias but low variability, what would, that's the top left corner here, high bias, low variability, what would that look like? So low variability means that they're going to be very close together, but high bias means they're going to miss the bullseye significantly. So, so bias in this case means that we're going to be off from the target, the bullseye of the target. Variability, high variability, means they're going to be more spread out. So in this case, part A, it says high bias, low variability. The arrows are consistently going in the same spot, but that is just way off. So it's high bias, low variability. All right, going across B, we want to say, okay, so what would it look like if I shot a bunch of arrows at the target and I had low bias but high variability? All right, so they're very much all over the place. I didn't really hit the bullseye at all, but the average of all of them is the bullseye, right? So if you took all of those and averaged them together, then we talk about, oh, it's centered right at the bullseye. However, they're high variability. They're spread out pretty considerably. All right, C says high bias and high variability. Well, that would just mean they're not clustered together. They're high variability and they're way off from the bullseye, so high bias as well. So this is sort of the worst of the situations. And then the ideal situation is no bias or low bias and low variability. So that means they're all hitting the bullseye. They're all, and they're very small variability. And that's what we want. We want our estimates to be clustered together. And we also want all of our estimates close, not just close clustered together, but closely clustered around the true parameter or the proportion or mu that we're looking to estimate. All right, and this is the homework due next class.